Hello scholars, and welcome to this Chapter 2 review video. I have selected a few problems for us to go over on this video, and of course I'll be doing plenty others in class, as well as you have also had the opportunity to review with our extra credit assignment. So let's get to it. You will see evaluating functions on our test on Tuesday. So if we're given f of x is equal to the opposite of x squared plus 3x minus 4, remember that function notation is nothing more than a set of instructions telling you what you're going to do with an input. So our first input value is going to be -4. Remember, you really cannot overuse parentheses here. It's always wise to snuggle up our input value inside of those parentheses. So we're going to follow order of operations carefully here, which means that we are first going to square it. So remember, this is like having a -1 out front, so -1 times 16 plus 3 times -4 minus 4. I'll move to the right. Now we're going to multiply, and we get -16 minus 12 minus 4. So -16 minus 12 is -28. -28 minus 4 is -32. So the function's value when x equals -4 is -32. Let's keep going, and now let's plug in this expression t plus 2 as an input. So the opposite of t plus 2 squared plus 3 times t plus 2 minus 4. We're squaring it, multiplying it by 1, multiplying it by 3, and then subtracting 4. That's what we're doing to the input when we evaluate this function. So follow order of operations again, which means this binomial needs to be squared first. So when we square t plus 2, we get t squared plus 4t plus 4, which we will multiply through with a -1 plus 3 times t plus 2 minus 4. So now let's distribute that -1. Negative t squared, -4t minus 4 plus 3t plus 6 minus 4. So when we find those like terms, there's a t squared, there's a t, a constant, and a constant. Let's put those like terms together. So bring down the t squared. So -4 plus 3 minus t, -4, a positive 6, and a -4 is going to be a -8 plus 6, so that is a -2. So this is the evaluation of the function when x equals t plus 2. Next, you're going to have to graph a piecewise function. So what we've talked about, and you can go back and watch subsequent videos, is we look at what is special within the given domain restrictions. So it's telling us that there is going to be something magical right around here. So remember, we're dividing the domain up into everything less than 2 as well as everything greater than or equal to 2. So everything left of this auxiliary line, we're going to use the first function. Everything to the right of the auxiliary line, we're going to use the second half of the plane. So here we go. Let's start plugging in. So both of these are quadratic. This is particular quadratic function has a negative leading coefficient, so that means on this side of the auxiliary line, it's going to be going down. This has a positive leading coefficient, so on the right-hand side of the auxiliary line, it's going to be going up. So two parabolas are essentially what we're going to be graphing here. So g of x equals -1/2 x squared when x is less than or equal to 2. So let's make a little xy chart so we can get some precise points here. So obviously Since we have to multiply by a half, I'm just going to choose some even numbers here. So -4, -2, and 0. And so let's plug those in. -4, g of -4 is going to be -4 squared, which is 16, and -half of that is -8. Now, that is not quite going to fit on our graph, so let's see. If that's 6, that's 7, so it's somewhere down here, right on the very bottom, which I'm just kind of denoting with a dot there. So if we plug in a -2, let's plug in a -2. G of -2, -2 squared is 4. Half of that is -2. So that we can graph pretty easily here. And then, of course, g of 0 is going to just be 0. 0 squared is 0, half 0, 0. So we are going through the origin. Now, we talked about this in class. Even though this says x is strictly less than 2, if I plug in 2 into this top function, 2 squared is 4, half of 1 -half of 4 is -2. I am going to have an open circle right there. So here is what my parabola is looking like. But it's just going to stop there, remember, because that's on the auxiliary line. So now on the right-hand side of the auxiliary line, we're going to pick up the second piece of the function. So this time, x is equal to 2. So I'm going to put in 2 into the second function. 2 squared is 4. 4 times 2 is 8. 8 minus 4 is 4. So over 2, up 4. And that is a point. Now the next one, and this is immediately going to get crazy. So let's plug in a 3. Because if we have an a value of 2 here, we see this parabola on the bottom has a horizontal stretch, also a vertical compression, same thing. So basically it's getting fatter and flatter right there. This one has a vertical stretch, so it's going to get taller and skinnier. So when I put in a 3, 3 squared is 9, 2 times 9 is 18, 18 minus 4 is 14. So immediately this is going to take off in that direction and not even fit on my ghetto graph paper here. But that is what this piecewise function would look like. The key is realizing where the line of demarcation is right here between the first piece of the function and the second piece of the function. Next, given the function f of x equals 3 over 2x minus 1, let's start by finding the domain. Of course, this is a rational function, and a rational function simply has a fraction bar. And we need to take whatever expression is in the denominator and set it equal to 0. And when we set it equal to 0, we get x equals 1/2. Now what's really happening there is the fact that we are going to have a vertical asymptote at x equals 1/2. And we will be touching more on that in chapter 3. But what that also tells us is that we have a restricted value within our domain. So the domain is all real numbers except 1/2. So when we write the domain in interval notation, it will start from the left at -infinity, go to 1/2, jump over 1/2, and then go to positive infinity. The next thing that I would ask you to do is to find the inverse of the function. So if this is our function, I think I can fit the 4 steps right in here to find the inverse. Remember, the inverse notation is f to the -1 of x. F inverse of x. That's the notation. So first step, replace f of x with y. There you go. Next step, that's step 1. Step 2, switch the x and y. X equals 3 over 2y minus 1. Step 3, solve for y. So the first thing I'm going to do here in order to solve for y, I'm going to put that x over 1, and I'm going to cross multiply in order to eliminate the fractions. So we end up with x times 2y minus 1 equals 3. So from here, we need to distribute that x because we need to get rid of those parentheses because we're trying to solve for y. So that gives us 2xy minus x equals 3. Remember, we're trying to solve for y. So I need to first take the x to the other side, which I'll continue moving in this direction. So 2xy equals 3 plus x. And then the next step is to solve for y by dividing both sides by 2x. So y equals 3 plus x over 2x. So step 1, replace f of x with y. Step 2, flip the x and the y. Step 3, solve for y. And here's step 4. Step 4 is to write it using inverse notation. So f inverse of x equals 3 plus x over 2x. So here is the actual inverse. Now, we're going to verify the inverse by asking this question. Does f of f inverse of x actually equal x? That's why I've got a question mark right there. So we're going to test this by using a composite function. So f of f inverse, well, this is f inverse. So we're going to plug 3 plus x over 2x into our given function f and evaluate. So f of 3 plus x over 2x. We're composing the functions. So what does the f function tell us to do? Well, here's the f function one more time. It's 3 over 2 times the input minus 1. So our input in this case is the inverse function. So it's going in right there. 3 over 2 times 3 plus x over 2x minus 1. This is the fraction that we need to simplify. So let's do it. So following order of operations, I'm going to work on the bottom of that big fat fraction bar and just covering up the numerator. The fraction will be the last thing we deal with. So we end up with 2 over 1 times 3 plus x over 2x. First thing I see is that those 2's are going to cancel, leaving us with 3 plus x over x minus 1. That's all underneath the 3 that's on the top that I'm about to lose right there. So let's keep going working on this denominator. Now, the next thing to keep in mind is this x is the denominator for both of those terms. So let's move to the right here. We've got 3 on the top over 3 over x plus x over x minus 1. Of course, x over x is 1. So basically, all of that fraction becomes 1, and we end up with 1 minus 1. And 1 minus 1 cancels to 0, and now we've got 3 over 3 divided by x. Of course, division by a fraction turns into multiplication by the reciprocal. Now the 3's cancel, and we get x. So, does f of f inverse equal x? Check, it does. That is how you verify the inverse with the composition of f and f inverse. If you go in the other direction, f inverse of f, it will also give you x as well. Number 4, graph g of x equals 2 times the square root of negative x plus 3 plus 4. So when we're graphing a square root function, an even root function, and every even root can be rewritten as a square root. So if we have a square root function, the first thing we're going to do is take the expression that lives underneath the radical sign, and we are going to set it greater than or equal to 0. So negative x plus 3, this expression must be greater than or equal to 0. So when we solve it, we get negative x is greater than or equal to negative 3, divide by negative 1. We are dividing by a negative, which flips that sign. So we end up with x is less than or equal to 3. So our domain is all real numbers less than or equal to 3. So that's negative infinity to 3 with a bracket. So when we go to an XY chart here, that gives us our starting point. So we're going to start with 3 and we're going to choose numbers less than that. But let's choose wisely because this is under a square root. So we want to choose values for x that are going to eventually yield a perfect square. So if I choose a 2, that'll be helpful. If I choose a negative 1, it will also be helpful. And that's probably all the numbers that we need. We really just need 3 or 4 to be pretty precise here and see the general direction of this graph. So let's plug in a 3. So g, put it over here, g of 3 is 2 times the square root of opposite of 3 plus 3 is 0 plus 4. So the square root of 0 is 0. 0 times 2 is 0. 0 plus 4 is 4. So 3, 4, which makes sense because this whole graph should have a vertical shift up 4. So 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. So this is our starting point. So think about what this graph is going to look like. So it's going to be going in this direction and it's going to be going up. Maybe I should have made that a negative 2 so it would be going down according to the way I drew my graph. But we'll make it work. Here we go. Let's plug in the 2. G of 2. G of 2 is going to be 2 times. Opposite of 2 is negative 2. Negative 2 plus 3 is 1. Square root of 1 is 1. 1 times 2 is 2. 2 plus 4 is 6. So over 2, and I'm going to draw my graph a little longer here. There we go. 5, 6, 7. So over 2, up 6. And let's see if we can even squeeze the negative 1 on there. G of negative 1. G of negative 1. 2 times the opposite of negative 1 is 1. 1 plus 3 is 4. The square root of 4 is 2. 2 times 2 is 4. 4 plus 4 is 8. So negative 1, 8. So basically, yes, here is what my graph looks like. Something like that. So obviously, I meant to draw in that direction and I blew it, but that's all right. What is our range? Our range, does this graph have a bottom? Yep, the bottommost value. Remember, the range has everything to do with the y-axis. So the range begins at 4 and then goes up forever, so that's 4 to positive infinity for the range. Last problem. Rewrite the equation of the circle in standard form and find the center point and find the radius. So first thing we're going to do, we're going to group everything that has an x together, and we're going to group everything that has a y together, and then we are going to push that constant to the right-hand side. So we're using the associative property and the commutative property when we change the order and change the grouping. So x squared minus 8, 8x plus y squared plus 20y equals negative 44. So this is our first step. Remembering that our standard form of a circle looks like this: x minus h squared plus y minus k squared equals r squared. Everybody has to know that. So next, we're going to complete the square for the x's and the y's, because our goal is to have a factored expression for the x's and the y's. So we're going to complete the square. So x squared minus 8x. Half of 8 is 4. 4 squared is 16. And if we add it on the left, we have to also add it on the right in order to keep our equations balanced, or our equation balanced. Let's do it again. So y squared plus 20y. Half of 20 is 10. 10 squared is 100. Plus 100 plus 100. So now we've got two perfect square trinomials that we can easily factor. Factors of 16 that add up to 8 are 4 and 4. Next, factors of 100 that add up to 20 are y plus 10 times y plus 10. Negative 44 plus 16 plus 100, that is 116 minus 44, that is 72. So now we have rewritten our equation in standard form. What's our center point? We've got the opposite of negative 4, which is 4, and the opposite of positive 10, which is negative 10. That's our center point. Remember, our center point is HK. And this guy over here, of course, is r squared. So if r squared is equal to 72, we want our radius in simplest radical form. Therefore, r equals 70 root 72. That's 36 times 2. That is 6 root 2. There's our center point. There's our radius. There's our equation in standard form.